Yes, thank you, Misha. So today I will try to show that trion-polaritons are indeed very interesting system for unconventional photon blockade. So I'm coming from Exeter, which is located in a beautiful part of England. It's southwest, and it's an excellent university. So if you want to join the team, please write me a message. I have a postdoctoral position available exactly into deep polaritonics. So of course, PLMCN is all about polaritons. And why do we work with polaritonics? Historically, because of effects of condensation. So that was fundamentally interest of polaritons. But later we asked, can we make some applications with polaritons, and starting from nonlinear circuits to terahertz sources and lately to topological polariton lattices, that was all about getting some new applications. And why do we love polaritons? Because they're pretty easy to work with experimentally as compared to cold atoms or microwave circuits. They operate at relatively high temperatures, but most importantly, they are nonlinear. They have sizable nonlinearity. And if a photon-like particle, polariton, has nonlinear properties, we can ask a question, will we feel this nonlinearity at the level of two excitations? And can we drive polaritonics in the quantum regime? And that, I guess, will be the ultimate goal of every quantum optical system. So polaritons interact through scattering of two excitons, and this corresponds to a Kerr effect. So this nonlinear interaction does the following. If we try to excite two polaritons, nonlinear interaction shifts energy up, so we cannot create this state. And effectively, we remain with 0 and 1 excitation, which can be seen as polaritonic qubit and leads to blockade physics. And already some time ago, KYRIIENKO and Oleksandr has shown that, yes, if we have interactions, we can reduce second order coherence G2 function to 0 and have single photon or single polariton physics. You could see there is an anti-bunching window in certain level of the tuning and the bunching. And also if you have large nonlinearity, so U over decay rate kappa is large, you have nearly 0 G2. So that corresponds to anti-bunching. But we can also ask, is it easy to achieve? So for gallium arsenide, interaction constant is of the order of 6 microelectron volt micrometer squared. And if we consider the micropillar geometry, it would require 200 nanometer diameter for the pillar to actually get the blockade. And that's very challenging experimentally. So unfortunately, for some time, people believed it's impossible to study quantum effects with polaritons, but this starts to change. And to really drive polaritonics into a new regime, we need to improve the quality of structures or come up with some new schemes and effects. And that's what was done previous year in two publications in Nature Materials. So two groups independently created high quality microcavities and reached the quantum regime. How did they do it? By simply reducing the kappa, so the decay rate of the mode, and having very small mode volume. What they have achieved is a G2 of 0.95, so just 5% anti-bunching. It's enough to claim that we are in a quantum regime, but it's not enough for applications. And of course, you cannot improve the system forever. So we can ask, what are the options? One option is to actually have unconventional photon blockade. So it was proposed some time ago by Timothy Liu and Vincenzo Savona, where they say if there are two modes that are coupled to each other with even small nonlinearity, so U can be smaller than decay rate, but large tunneling, you can get a single photon emission and suppress two photon contribution. How do you do it? First, you have an excitation path which is direct for photon. So you just pump the photon up. But you also have indirect path through the second pillar, which is nonlinear. And these two passes will destructively interfere. So in certain region of parameters, you can have G2 going close to 0. It is very sensitive and difficult to control, so that's why it was not easily achievable with polaritons in this geometry, but it was checked in microwave systems and quantum dot systems. So what else can we do is actually study new materials and study new setups. And recently there were many works on TMD polaritons. So we have two-dimensional material, transition metal dichalcogenide. You put it in a microcavity and you can hybridize modes efficiently. And in these materials, it's easy to observe Rabi splitting, which is actually quite large. It goes up to 50 millielectron volt. But if we look what will be the interaction constant, that will be my main interest, we see that it actually reduces as compared to gallium arsenide by almost an order of magnitude. Why is it so? Because excitons in TMD materials are small, so the scattering cross-section is small. And it's nice platform for light matter interaction, but not so much for nonlinearity. Or we could actually look more carefully what are the nonlinear mechanisms for TMD polaritons. So that's an experiment which was done in Sheffield by the group of Dima Krzyżanowski and Mariusz Szkolnik, where they put a layer of molybdenum diselenide in the microcavity, and they observed anti-crossing with exciton mode, but also another anti-crossing in this part of the spectrum, which originates from a trion resonance. And this trion anti-crossing was reasonably large at small pumping, but if you increase the pump for photons, they have seen the collapse of strong coupling. So how can we explain it? For instance, with nonlinear saturation effect. We say that trion Rabi frequency is indeed a function of a pump, or in our cases, a function of the number of trions. And if we simply fit this nonlinear coefficient, we will see it's actually rather large. It's bigger, much bigger than the Coulomb exchange effect, and it's comparable to gallium arsenide. So it's 40 microeV micrometer square. And the question arises, can we maybe reach a quantum regime with trion polaritons and nonlinear saturation? So we can build a theory by saying that trions is a combination of two electrons and a hole. And you need to imagine that exciton is created by a cavity photon. It picks up an electron from the Fermi sea, but it also leaves an empty state there. So altogether, we convert cavity photon to trion and electron excitation with some coupling constant G. We could use the definition of trion electron pair, so and it will be quasi-bosonic operator B, and overall coupling will reduce to just two modes, cavity photon coupled to trion excitation, with Rabi frequency, which now becomes amplified by square root of the number of electrons. So that comes from superradiance effect. However, this excitation B is not a pure boson. If we look at commutation relations, at the small number of trions for small occupations, it does have a bosonic commutation relation, but it will change if we start to populate the system. Why? Because of the phase space filling effect or nonlinear saturation. So trion and electron are not bosons. It's a composite boson, and we need to account for the increasing number of fermions. It's not a boson anymore. And this effect is large in TMDs because the light matter coupling is substantial in this system. So we can build a Hamiltonian from matrix elements, and most importantly, there will be off-diagonal matrix element which connects two states. So if B was a boson, it will be just square root of NT in front, so bosonic enhancement. But because of the saturation, we will have the following perfector, which is quite large. And the main message is if NT over NS becomes large, we can collapse the coupling. So that was the origin of observed effect. But we could also study single photon physics. And if you are interested in the theory, please check our archive, or soon it will be published in PRL. Now let's calculate what will be the second order coherence in this case for zero delay. And to understand how it behaves, we can look in the level structure. So photons can be excited up and they can be converted to trions. And the coupling between a photon and trion will be diminished if we have several trions. We could also look in the rest state picture, saying that there will be trion-polaritons with some energy, for instance, lower and upper polariton. And if we drive just lower polariton, because of reduced coupling, this state becomes unresonant, so we have conventional blockade. And that's what we observe in the following plot. We see that G2 has a funnel life shape profile as a function of pump, so like in conventional case, and G2 drops as a function of coupling. So we can have conventional blockade. We have reasonably high cavity occupation, and it behaves as we expect, but it requires a strong light matter coupling at the single trion level. So it puts like strict conditions for cavity mode, line width, and also for trion. So can we improve on that? Turns out yes, and surprisingly, doing this calculation, I have found that there was a region where G2 drops. It happens at very different detuning, so it should be resonant to a cavity mode, and there were two windows. So how do we understand this effect? We need to think of original picture. So first of all, we can excite two photons into the state with zero trions, and we have another excitation pass through the trion with effectively nonlinear coefficient. So we can get the same unconventional blockade for the case of trion-polaritons, and this will happen for coupling, which is of the order of line width. So it shouldn't be much larger than in conventional blockade. So we also built cavity occupation emission rates, and of course they are reduced compared to conventional blockade, but they are not that small. So in principle, you could use it for single photon emission, and it will be better than polaritonic molecule. We have also built an analytical theory to estimate optimal parameters at small pump. And this is a correspondence between analytical theory and master equation. We see it matches really well. So the optimal parameters become slightly shifted from cavity resonance. And importantly, we find that these optimal parameters do not depend on electron concentration. It will always stay the same. If we plot G2 as a function of trion-photon coupling, we will see that it has two regions. First corresponds to unconventional blockade. So if we scan over all the tunings and find the minimum, this will correspond to unconventional blockade. It doesn't depend on the number of electrons we have in the system or concentration. And there will be a region for large GC corresponding to conventional blockade. This will be dependent on concentration, and it favors smaller concentrations. So together with these two anti-bunching windows, we can ask the question, what will be the second order coherence function as a function of delay? And G2 slowly grows from 0 to 1 for conventional case, and it oscillates for unconventional blockade case, which is a known result. So this oscillation will be proportional to the square root of the number of electrons, but we can see for realistic conditions, these oscillations are not too fast, and they can be resolved with modern detectors. So let's do some estimates for the coupling. And interband matrix element for TMD materials is actually quite large. This is the origin of large Rabi splitting. So material properties help us. If you consider a cavity which is reasonably small, we would get interband matrix element, which is quite significant. We will multiply it by the fact that trion is a bound state, and for electron density of 10 to the power of 10, we could have a significant coupling. If we plug it in for parameters of state-of-the-art cavities and rather broad trion line, we would obtain antibunching of the order of 95%. So it's much better than we had before with gallium arsenide. Of course, we could also try to reach conventional blockade. For instance,
1 minute.
Yes, sure. Where we go to low temperatures and high quality cavities. And that will be possible in the future. So again, you can check all the details in our preprint. So my conclusions are that polaritons are great. The ultimate goal for quantum polaritonics is to be in nonlinear regime and possibly reach photon blockade, and unconventional blockade with trions may be one of the ways we can do it. So thank you for connecting, and I'm ready for questions.
Thank you very much. Thank you very much, Oleksandr, for this very interesting presentation. The paper is open for discussion. Questions, comments, please. Maybe I can start the discussion. I do not see raised. Okay, I see one. Dima, please.
Yeah, well, just a small question. Maybe I just did not manage to understand. It's about, well, you were speaking about trions and electrons. So it's really trion-electron interaction, or it was because or it's exciton and electron which make trion? Well,
so it's not an interaction in the sense of Coulomb interaction. Of course, it will be there. Trions are formed by Coulomb interactions. They will interact with electrons. It's all in the system. We do not account for these effects. We account for something much more simple, which is...
Well, yes, at the slide number 11, for example.
Yeah.
Yes, you have a couple of a trion and electron. So in total, there are four particles. Exciton, which is made of electron and the hole, and 2 electrons.
So
it's
maybe here it's easier to understand. So trion is a combination of 2 electrons and a hole. And formally you say, I create a trion by creating 2 electrons and a hole. But exciton is a photo-created electron-hole pair. So you convert cavity photon to an exciton, but you also have an electron which changes the momentum. So you will call, okay, this composite operator, trion, but an empty state in the Fermi sea, will be my excitation. And they are not bound by Coulomb effects. This is the way you define the quasi-particle. So you are allowed to do it. And it's actually not that bad approximation, because we see trion-polaritons as a 2-coupled oscillator. So it works, but it just fails to predict what happens if you start to populate more and more trions, because it was a fake excitation in some sense. It's an approximation. And it's very similar to interband polaritons. It's interband polaritons, they are intersubend, they are kind of quasi-particles, but they are not bound to each other with Coulomb.
Well, I will try to ask you later, or just read your paper, because yes, I still did not manage to understand, but thank you very much.
Well, as far as I understand, the effect is simple. The trion oscillator strength is proportional to the number of electrons in the system. So if you have a few electrons, then the trion oscillator strength saturates very fast as compared to that of the excitons. And I think that this trick, by multiplying the electron annihilation operator, is just to properly write the light matter interaction.
Yeah.
Okay, so it's a kind of mathematical representation.
Well, I think so. Other questions or comments? Maybe I have a very quick one. So although the total system is electrically neutral, what about trion-trion interactions, because in principle the trions are charged, so you might see some blue shift due to the generation of trions in the system.
Yeah, this is a good question. It should be properly accounted. So it's not an easy problem to find what will be the trion-trion interaction. And I would say that experimentally, in the experiment, what we have seen is first a collapse of trion-Rabi splitting and then the rise of the blue shift. So what you are saying, the trion-trion effect might happen, but already after collapse region.
Okay, thank you.
And
I think that there is the last question by Ronan, please.
Yeah. So thanks for the talk. My question is, so obviously when you increase the number of electrons, you increase the Rabi splitting as a square root of the number of the electrons. But did you take into account also that you increase the relaxation rate or dephasing rate due to the interactions of the charged polaritons with the electrons? So not just in the sense of the phase space filling, but there's also a dephasing mechanism which would then broaden your line width, and as a result will reduce your visibility of your G2.
Yes, good question. So we do account for dependence on phase space filling. We don't account for increase of the phasing in the case of large number of electrons. But what I should say is that we try to stay in the situation where the number of electrons is low, so it's dilute electron gas, and we only have few excitations in the system. We don't try to reach this collapse of Rabi splitting. We really want to work with 0, 1, 2 excitations. It will require a very clean system, I admit. So you cannot imagine just some like noisy environment, but I guess it should be possible.
Okay. Thank you. I think that we need to stop the discussion right now, and let us thank the speaker once again.